Welcome everybody to the 2024 Glossop Medal Lecture and Glossop Award. I'm Anna Morley, the chair of the engineering group of the Geological Society, known amongst our friends as EGGS. And as you know, we're here in the historic Royal Institution Lecture Theatre, which is just a short walk away from the Geological Society. So we've got no fire alarms planned today, but we've got some exits, one down there, up there, and two here. So our speakers will be out first. They will be absolutely fine. I'd like to welcome Emma Slack, representative from Rudolph Glossop's family, and also the family of Dr. Mark Lee, our Glossop lecturer, and Jordan Weddepohl. He's got his family here today as well. So finally, Jordan, I'd like to invite you to come up and give your early career award lecture. So Jordan, over to you. Thank you.
Very much. Hello, my name is Jordan Weddepohl. I'm a senior chartered geologist working at Arup in the Sheffield office, and today I'm going to be presenting on the UK levelised cost for geothermal heat and power. And this is a piece of work commissioned by the Department of Energy, Security and Net Zero in the government. So first and foremost, what is geothermal? So it's effectively the energy exchange with the ground. So this forms generally two technology types. We have shallow ground source heat pump technologies and deep geothermal technologies. So the shallow ground source heat pump technologies are defined as being less than 500 meters deep, and they include closed loop systems, which is heat transfer via conduction, and then open loop systems, which are via convection. You abstract water, pass it through a heat exchanger, and then re-inject that water. These systems typically use ambient loop temperatures, so ambient ground temperatures, so maybe between 15 to 30 degrees, and you can extract heat in the winter, and then you can also re-inject heat in the summer to provide cooling for the system you're providing. Under these conditions, you can recharge the ground and use it as a thermal store, and that is the most optimal way to use shallow ground source heat pump systems. For the deep geothermal technologies, these can extend, or are defined as being more than 500 meters deep, but can extend to 1, 2, 3, more than 5 kilometers deep. And these use either deep aquifers, where we get favorable permeability and porosity systems, or we can have enhanced geothermal systems, where you drill a well, stimulate that well with hydraulic or electric fracturing to generate that artificial reservoir. And where you go significantly deep and you have favorable geothermal gradients and temperatures at depth, you can generate power as well as heat. So the second component is, what is a levelised cost? So a levelised cost is the life cycle cost of an energy generating system. So this is, we have levelised costs for electricity, LCOE, and also a levelised cost for heat, LCOH. And this is expressed as the pounds, or the cost for that asset, divided by the generation of that asset. So it's in megawatt hours of either heat or megawatt hours of electricity. And just to provide some geothermal context of where we are in the UK and why DESNZ and the Department of Security and Net Zero commissioned this piece of work, is the UK is very far behind the curve. Globally, we have over 100 gigawatts of installed heat capacity for geothermal systems and around about 16.5 gigawatts of installed power capacity. Currently in the UK, in January next year, we are looking in the UK to commission the UK's first geothermal power plant, a 3 megawatt system at United Downs. And there are ongoing discussions for deep geothermal heat. However, they haven't really been realised at scale yet. Contextually, in Germany, we have around about 400 megawatts of installed heat, geothermal heat, and in the Netherlands, they're leading the way. In Europe, they're looking at around about 1 gigawatt of installed heat capacity by 2030. So the purpose of this study is it provides the first levelised cost of heat model conducted for geothermal systems in the UK, and also provides a revision to the existing levelised cost for electricity model. And it's hopefully going to be used to inform policy-making decisions with quantitative data, which they can be used to compare comparable technologies. So the scope of this work was to generate those cost models and also to provide some UK context. So some of these systems, such as closed-loop systems, they work relatively comparably, regardless of location. However, systems such as open-loop and deep hydrothermal, they are location-dependent. They are targeting specific aquifers and reservoirs that need favourable permeability and porosities to get those sustainable flow rates and favourable temperatures. This was all informed from a global stakeholder exercise. We invited 440 global stakeholders to a questionnaire, and we also held almost 30 one-to-one interviews. We also undertook an extensive literature review, data compilation and cost modelling exercise, and additionally undertook a lithium brine mining exercise and whole life carbon assessment, which I'll get onto later. So this is the general workflow of how things worked. As mentioned, we undertook that data gathering exercise via those stakeholder surveys and one-to-one interviews. We also used literature, extensive review of literature, and also Arup's in-house data sets. The capacity estimates were, as I previously said, many of these systems, they work comparably regardless of location, so we applied some general assumptions for those, and we undertook a UK-wide geothermal assessment for some of those deep systems, which I'll get onto next. These system capacity estimations provided the heat and cooling potential and also the power potential. All of this technical data was then passed into the cost modelling exercise, which captured technical data, cost data, and financial data, such as hurdle rates and learning rates, and ultimately output these levelized cost of electricity and levelized cost of heat models. We also provided some indicative qualitative assessment of various funding mechanisms which could be applied via the UK government to help facilitate and bolster that supply chain and upscale geothermal in the UK. And additionally provided that whole life carbon assessment and lithium brine mining. So the UK geothermal assessment, I assessed 7 different locations to provide geographical spread. These included 5 sedimentary basins and 2 granite bodies. The granite bodies are typified by a greater geothermal gradient. So places like Cornwall might have geothermal gradients of 40 degrees C per kilometre. So you have to go relatively shallower depths to get those higher temperatures compared to areas where there are suppressed geothermal gradients. Other areas such as the Cheshire Basin and Wessex Basin were highly informed from oil and gas and 2D seismic survey data compared to some of the other regions which were potentially less informed. So I'll just show an example of some of the assessments we did for each of these regional contexts. So this is a stratigraphic column I produced based in Portsmouth for the Wessex Basin. It was informed from the oil and gas local wells and also 2D seismic data. We produced this information to outline the depths of the target reservoirs and also outline which of the target reservoirs we would target for a hydrothermal system. So in the case of Wessex, it would be the oolite groups and also the Sherwood sandstone groups at depth. Then a review of the literature data provides the permeability, porosity, KH, KV values, and other various hydrogeological parameters which we require to undertake this geothermal assessment. I plugged all of this information into Doublet Calc, which is an industry standard heat capacity estimation tool, to provide this probabilistic curve where P90 represents the 90% chance to achieve, P50, 50%, and P10, 10% chance to achieve. So for each area, we have a low, medium, and high value, which we can then plug into the levelized cost models to provide that low, medium, high levelized cost range. Now, unfortunately, I can't share the bulk of this information with you yet because it has yet to be published. This report has been ongoing for over a year, and we're in the latter stages of publication now, working with DESNZ to actually get that out, and hopefully it's going to be produced early next year. But it will contain all the technical data, cost data, financial data. There's been a lot of modelling undertaken, many of which has been automated, a lot of variables applied, and hopefully this will provide a really robust and reasonable data set, which industry personnel, politicians and like can inform decision making and hopefully bolster the UK's geothermal sector. Now to something that I can present on, which is the whole life carbon assessment. So whilst the government is very keen on money, and money drives everything, they also have very ambitious net zero carbon targets, for 2050. And like the whole world, we should be really pushing to use low carbon heating and low carbon power technologies. So what is a whole life carbon assessment? It is capturing all the capital carbon costs, so that's all the metal that goes in your casing, the concrete carbon intensities, all the plant infrastructure costs, the conveyance piping carbon intensities, combined with the operational carbon, so that's the amount of carbon you use by running the electricity. Each electricity is provided by the national grid, and there's a carbon factor applied to the national grid electricity value. So currently that's value X, and by 2050 they're looking to reduce that to net zero. So on day one of operating a geothermal asset, we might have a very high operational carbon intensity, but hopefully by the end of that, we will have surpassed our 2050 net zero carbon target in the UK, and that asset will be operationally carbon neutral. And then at the end of the life, we also have to decommission the wells. So the regulators, the Environment Agency, the North Sea Transition Authority, and HSE, they don't like to leave assets open, so we have to plug these with concrete, which again comes with a carbon cost. So what are the results? So what we find is that the shallow systems at scale, if you ignore the closed loop 1 borehole, so the 20 borehole, 100 borehole, and the open loop systems, they're relatively low carbon, at around about 20 kilograms of CO2 equivalent per megawatt hour output, and that's a thermal output of heating and cooling combined. And then if we then look at the deep geothermal stuff, we get 1 kilometre, 2 kilometres, 3, 4, and 5. You see that nice decreasing trend. And this is principally because with depth, you get greater temperatures, and if you can sustain that high flow rate, you get greater heat capacity. So you get more bang for your buck with less carbon intensity the deeper you go, based on the information we've seen here. As you can see, operationally, that seems to be the most intensive phase. These assets are operating for a 30-year life on average, so they're running a lot of electricity. But as previously mentioned, the day one electricity use is going to be far greater than the 30-year energy use. We also provided a contextualized air source heat pump assessment. However, that only assessed the operational carbon. But all of this, relative to gas boilers, they are about a magnitude less carbon intensity. So gas boilers have a very standard calorific value, and that is around about 215 kilograms of CO2 equivalent per megawatt hour of heat output. So we need to move away from gas as fast as possible, and geothermal appears to be a very low carbon and suitable technology to take on that role. And then finally, moving on to lithium. So lithium brine mining is a really growing, exciting, expanding industry in the UK and globally, where the geothermal brines, which are produced at depth, they can have very high concentrations of lithium. We're talking around about 100 to 400 parts per million. This can be extracted at surface and converted to a lithium hydroxide or a lithium carbonate component, which can then be sold to battery manufacturers and sold at profit. Obviously, this is a monetary revenue stream and can act to reduce levelized costs for those assets. It's quite a nascent and juvenile technology in the UK and globally. So there's limited information here, and you can see that the inferred models that I've undertaken are very straight line and very indicative. For this, I looked at pilot plant scale, which is hundreds of tons per annum output, a semi-commercial plant, which is thousands of tons per annum, and a commercial plant, which is tens of thousands of tons per annum. I assumed a linear lithium revenue, which is unsuitable. Lithium prices are going to be volatile, but we didn't model that. And also, it assumes that lithium production is stable over the life of the system. Now, that's highly uncertain. These lithium resources have been building for millions of years. If we extract at a very high rate, we could deplete that resource in a year. We could also deplete it in 100 years. We just don't know. So there's uncertainty here. So take these images with a pinch of salt. But it's interesting that the UK and a lot of sectors are looking at this. It has a potential to really be quite a money spare if you look at the commercial plant. So in conclusion, this study, and this has been a lot of information here, this study has been the first UK levelised cost of heat model undertaken in the UK for geothermal systems. We've also revised the levelised cost for electricity model, provided a regional context for different geothermal reservoir targets for deep geothermal capacity and heat and power capacities. Also undertaken lithium brine mining to indicate how that could reduce levelised costs, and shown that whole life carbon assessment, geothermal is quite a good candidate for reducing those levelised costs. Reducing the carbon emissions of heat and power generation assets. And ultimately, geothermal has a crucial role in enhancing the energy transition to renewable energy. And it would be great to see the government and policymakers really take this into effect, and hopefully we can develop a supply chain in the UK and really push the agenda for development at scale. And that's it. That's the end of the talk. So thank you very much. It's been a real pleasure.
Thanks, Jordan. I'd just like to invite David Shilston. I think you're going to introduce Dr. Markley. I'd like to invite you down, please. Thank you.
Honoured guests, ladies and gentlemen, good evening. It's a great personal pleasure to introduce Dr. Mark Lee as this year's Glossop lecturer. Mark has a BSc in Geography from the University of Durham and an MSc from the National College of Agricultural Engineering. Since then, in more than 4 decades of professional practice, Mark has developed a wide range of expertise and international experience, which he will share with us in his lecture this evening. In 2003, Mark brought this extensive knowledge together in a PhD that focused on developing a framework for risk assessment and management of coastal change and cliff instability. Mark has presented and published his work widely, as well as journal papers. He's been joint author of a good number of books. I will mention just one. It has a particularly prominent place on my bookcase as an introduction to the discipline of engineering geology. It is titled Engineering Geomorphology, Theory and Practice, published in 2007. It's a collaborative effort between Mark, Jim Griffiths, and Peter Fuchs, and is notable for the many illustrations within its 43 short but very readable chapters. I had an opportunity of working alongside Mark in BP's In Salah gas export pipeline project in the deserts of Algeria. We then became part of a geoteam that BP assembled for pipeline route work in Azerbaijan, Georgia, and Turkey. It was fascinating to witness Mark applying his engineering geomorphology skills across so many diverse terrains, including hot deserts, mountains, and plains. Working with him in the field, I was always impressed by his ability to read the terrain, to understand and assess Earth's surface processes, and to evaluate the hazards and risks they pose to a project and the wider environment. Mark has applied his terrain skills to many other projects, notably on coastal and marine engineering and landslide assessments. For these and many other projects, he developed highly effective geomorphology, maps, and process models, using them to convey his understanding of issues to members of project teams, including myself. In all of this, many people, including Mark, I'm sure, owe an enormous debt to 3 previous Glossop lecturers, Dennis Brunsden, Peter Fuchs, and Mike Sweeney. It now gives me great pleasure to invite Dr. Mark Lee to give the Glossop lecture for 2024 on the subject of landslide risk, radical uncertainty, and engineering geomorphology. Mark, the table is yours.
Thank you, David. There we go. So many of you will know this guy. This is Professor Dennis Brunsden, a great friend and mentor to me, probably a teacher for many people here. man for all seasons. He was a really internationally renowned academic geomorphologist. He was a pioneer of engineering geomorphology. He was a cider maker, and oh, would he tell you that he made cider, and a painter. And he was also one of the main reasons why the Jurassic Coast was established in Dorset and East Devon. And he was your 5th Glossop lecturer. Now, I wasn't one of Dennis's students. I first met Dennis in 1985 at an interview for a company that he'd set up with John Dornkamp, Ron Cook, and David Jones, other academic geographers as well. The company was Geomorphological Services. Fortunately, I got the job because it was there that I met Jim Griffiths. Oh, with hair. Yeah, with hair. Now, Jim is another important influence on my career. Together, we mapped the landslides in the Channel Tunnel portal areas. We went down to Torbay and did applied earth science mapping. But we also spent a lot of time working with Dennis and a big other team on the first national review of landsliding in Great Britain. And this is the database which has now been taken over, upgraded, improved, and managed by the BGS. Here's Dennis again, this time with Roger Moore. Now, Roger was one of Dennis's PhD students, and Dennis was really, really proud of Roger's achievements because of that. Roger has set up and run an engineering geomorphology team at Halcrow and now Jacobs. But in the 1980s and 1990s, we worked together on a variety of projects, including the ground movement problems in Ventnor, Isle of Wight for the Department of the Environment, the investigation and management of soft rock cliffs for the Ministry of Agriculture, now DEFRA, and also the coast protection improvements at Lyme Regis. Now, the coast protection improvements at Lyme Regis was the focus of Dennis's Glossop lecture, where he really talked about the role of geomorphology in supporting the design of the coast protection works. Now, my lecture tonight is really about the role of engineering geomorphology in supporting and developing landslide risk assessment. So, I'm Mark Lee. I'm a geographer, I'm a geomorphologist, and I'm also a landslide risk specialist as well. 2002, I think, well, it's over 20 years ago now, the first edition of Landslide Risk Assessment came out. It seems an enormous age ago. But the 3rd edition came out last year. The important thing that much has changed in the time from the early 2000s to nowadays. Concepts of risk have changed, and certainly my experience and knowledge have changed as well. So what we're going to get tonight is a bit about my journey through those 20 years, from the early days when I was swayed by the power of simple statistics, to a bit of an epiphany in Algeria, and then a realization that coastal systems and other places are really complex and may show signs of chaotic behavior as well. And then we'll wrap up with some lessons from Yorkshire, because we're from Yorkshire. And Yorkshire, God's own county, the Broad Acres, is where we're heading tonight, because we're going to look at coastal systems, coastal landslides at Scarborough, and these are occurring over 100 years, timescales, major events. And then we're moving down to Holderness, where you've got frequent landsliding occurring on a 1 to 10 year timescale. All the work is focused and is directed towards the understanding of economic risk on the coastline. And here's a really simple version of the risk model that we developed at the time. Probability of an event times the consequences. There are other bits that are important, but we need not go into them. Otherwise, I'll end up talking about discounting and net present value and things like that. But the work was done as part of the MAF research, and it was in support of the MAF's Project Appraisal Guidance Notes, Approaches to Risk. and it was done in conjunction with Jim Hall, who's now at the Bristol University, and Ian Meadowcroft, who I think is still with the Environment Agency. So the model that we developed is essentially built on this idea that you can extrapolate future probability from the historical frequency developed from a landslide inventory. Now, this simple model is based on a number of really important assumptions. The first one is that steady-state equilibrium occurs over the inventory period. And the second one is that the past and present are the key to the future. Steady-state equilibrium can be conflated with the statistical assumption that the observed frequency over time converges to a true frequency over an infinite number of identical trials, over an infinite number of identical trials. Now, the other important assumption is that you can call individual years a separate trial, and that's important because then you can use the frequency, historical frequency, to generate an annual probability. And equilibrium allows extrapolation or prediction through extrapolation without any geological knowledge, and it's almost like geology-free statistics. But, and this is the important message, once the geology gets involved, we start having uncertainty. And it's this relationship between statistics and uncertainty that we'll be talking about. So what is steady-state equilibrium? Well, it's one of those words that can mean all things to all people. For the engineers here, you're probably thinking of Newton's laws of motion or thermodynamics. But for the geologists, it relates back to the writings of Charles Lyell from the 19th century. And his view was a world in balance between process and form, unchanging through time, with a constant rate of processes. So steady state from a landslide point of view would be a uniform rate of landslide activity through time, a constant range of landslide types and sizes. That yields a predictable future and allows us the extrapolation. Now, this simple notion is really the root of a whole range of measures of landslide hazard that you'll see, like landslide density based on geology and slope angle, erosion contours drawn on the coastline, and also magnitude frequency curves, where you've got a plot of number of recorded events on the y-axis and the size of the events on the other axis. But many people now, myself included, believe that this equilibrium is little more than a metaphor for how we would like to see the world rather than how it actually works. And this is what we're really talking about tonight. So, what is risk? Gosh, December 2006, we're certainly exposed to risk that day. Now, shock can be a really, really strange thing. And I remember after the event sitting on the hill waiting for the rescue team to come along, and I'm thinking, what is this risk that we've been exposed to? Is riding in the helicopter a risk, or is it an activity with associated risks? And I'm pondering that for a while, and then this comes out, the definition of risk from the International Standardization Organization. Risk is the effect of uncertainty on objectives. Well, I've tried to explain that to clients on numerous occasions. But fortunately, it's stimulated quite a debate in the risk industry. And the Society for Risk Analysis has recently come up with a glossary of terms which I found a bit more palatable. The consequences of the activity and the associated uncertainties. So what is landslide risk? So these people, these holidaymakers sat on the beach here, They're undertaking an activity, we could call it they're relaxing, they're sunbathing, they're looking out to sea. But future events may occur. Obviously, we know that these are potentially rockfalls, and there can be consequences as a result of it. But there is uncertainty. Now, the uncertainty about the event can be associated with the timing, the location, and the size. The uncertainty over the consequences may be related to the number of people injured, killed, or whether anyone is actually there at the time as well. So we can express risk as a function of the event, the consequences, and most importantly, the uncertainty. The risks we're seeing here, the obvious one is loss of life or injury, but taken from a different perspective, maybe the perspective of the local authority, there's also the potential risk of loss of tourist revenue, if they close the beach and so on. We can measure the risk through the simple equation, probability of a hazard times the probability of the consequences. And the rockfall events that can come down are the sources of this risk, and hence the hazard or threat. Another situation, this is a gas pipeline running through a tropical jungle in Southeast Asia. The pipeline's running through this right-of-way here. Let me turn that off. So you never know who's going to call at embarrassing times. There we go. Right. So the pipeline's running through this right-of-way, the green strip. It's buried. It comes down from the crest into a gully and rises up the other side. Then, kaboom! Landslide occurs, pipeline ruptures, product is released, and there's an explosion. The risks: loss of life or injury caused by the explosion of the released product, costs associated with pipeline shutdown or repair replacement, costs associated with reputational damage to the operating company, impact on share price, costs associated with the environmental cleanup and any fines that they might get. And there are also risks associated with habitat loss and things like that. Using the same model that we had for West Bay, we have an activity, which in this case is the transportation of a product, gas. We have future events, landslides in the head of the gully, and we have potential consequences. And of course, we have uncertainty as well. So what are the elements of a risk assessment? Well, the obvious one is some form of hazard assessment, hazard analysis, when the important thing we're looking for is really the destructive potential of the landslides. And that may be related to things like velocity, acceleration, the mass involved, total displacement, and so on. We have a side called the consequence assessment, and this is really looking at the monetary value of the impacts, the consequences, or the number of fatalities, injuries, and so on, or even the environmental damage as well. But equally importantly is the uncertainty assessment. And the uncertainty can be expressed in terms of verbal narratives, or this is where the probability side enters into the notion of risk. So what is probability? Probability is a measure of uncertainty, and it converts all the uncertainty that you have into a single number, and that single number is often really precise. So it's like saying, I don't know anything about this, but it's 1 in 2,500. So it's like a little magic wand that you turn everything you don't know into a precise number. There are 3 interpretations of probability that are important. One is the classical probability, where there are equally likely outcomes. Second one is the empirical probability, where it's related to the relative frequency of events through time. And the third one is a degree of belief or a judgment. Now let's play a simple game and think about the probability of Manchester United winning the Premier League this season. they're a team that play association football. So from a classical probability point of view, there's a 1 in 20 chance that they'll win because all 20 sides have the same chance of winning. What do you think of that? From an empirical point of view, they've won the Premier League 13 times in the last 32 seasons. So the probability would be 0.41. So what do you think of that? That's assuming constant conditions. So Cantona's still playing. Giggs, Beckham, Scholes, Peter Schmeichel in goal, Sir Alex Ferguson is still the manager. They've got all that advantage and they'll have it for every year in the future. And that's delivering what is known as an objective statistic. And it's objective because you as the analyst are not adding anything to this. Everyone could come up with the same answer. But what about the degree of belief? Now, it may be even worse than that by now. But this is based on not only the history, but also up-to-date knowledge, experience, and so on. I think they've just changed their manager as well. So anyway, that is known as a subjective probability. There's something else that's important in understanding of probability, and that's the strength of knowledge. And we can have a strength of knowledge backing up the judgment of probability that may range from something that is strong all the way through to very weak. Now let's imagine this situation of Manchester United again, and you can have these guys. These are Sky Sports presenters and experts on association football. So they may have really strong backup knowledge for this. But this man and his 2 dogs, Tom in white and Leia in black, are actually Wigan Warriors rugby league supporters and have virtually no knowledge of association football these days. The equivalent for landslides, which is strong, maybe something like the north coast of Kent, north coast of the Isle of Sheppey, where Eddie Bromhead there, John Hutchinson and Neil Dixon have done decades of research on landslide behaviour. Very weak knowledge might be a situation like here in the Southern Highlands of Papua New Guinea, where we know absolutely nothing about the timing and frequency of events. So we can start representing our risk equation as risk being a function of the event, the consequences, the uncertainty, but also the knowledge that's available at the time of the assessment. Okay, now this debate about risk and uncertainty has been going on for many, many decades, and it has its origins in economics and the economics of risk and reward. Now, Frank Knight in 1921, Frank Knight was an economist from Chicago University. He wrote this book, Risk, Uncertainty and Profit, in which he identified 2 different situations. One he called risk and one he called uncertainty. For risk, the outcome was unknown, but the odds could be calculated because you have statistical data. Uncertainty, he called the situation where the outcome was unknown, but you have no data and you can't make an assessment of the odds. And he called the second case unmeasurable uncertainty. Now, of course, not everyone agreed, and Milton Friedman here, he thought that you could assign probabilities to both cases, frequentist probability, empirical probability to the risk case, and subjective probability to the unmeasurable uncertainty case. Now, a modern take on this is the book by the British economists John Kay and Mervyn King, and they coined the term radical uncertainty for this situation. And they called it a world of uncertain futures and unpredictable consequences, events whose determinants are not fully understood, making economic forecasting and quantification impossible. And it's this notion of radical uncertainty that we'll try and translate into a landslide side. So we're off to Scarborough, Scarbados, for those who are from the north of England. So it's the jewel of the north. So breakfast time, the 4th of June, 1993. We turn on the telly and Scarborough's premier hotel, Weddepohl, is toppling over the edge of this cliff. The phone rings, and it's Alan Clark, my boss at Rendell Geotechnics at the time, and he's basically saying, drop everything you're doing and get in the car and come with Roger Moore up and try and help map out this landslide because we need to do something for emergency stabilisation works. So Roger and I get up there, the hotel's collapsing, dropping off the edge of the cliff. No one was injured, fortunately, no one was killed, but it caused such a stir, both in Scarborough town, but nationally as well. The situation, if you look in the top left, you can see that the hotel is set back from the cliff edge. It's about 90 metres from the cliff top. So when the event happens, they lose 60 metres of cliff overnight, and another 30 metres are going by that early morning and subsequent day. The cliff has been purchased by the council in 1887, and then it was landscaped, drained, and this network of footpaths was laid out so the Victorian tourists could perambulate around and enjoy the scenery. A seawall was built in 1893 for the pricely sum of £1,400. Gosh. Weddepohl itself was built as a private home in 1879 and then became a hotel. So we're there. The cliff comprises a sequence of glacial deposits, 30 metres of them, over Scolby Formation, Jurassic Scolby Formation bedrock, 30 metres of that. So 60-metre high cliff. And this is a copy of the geomorphological map that Roger and I produced. Now, this has been languishing in a box file in my loft for, it's over 30 years now. But this is what we did. So we've got in the front, we've got this big, broad spread of debris stretching 100 metres across the shore platform, and a series of detached landslide blocks retrogressing up the slope and surrounded by this really steep, prominent backscar. The council, over the next week or so, were fortunately able to track down a number of fishermen and late-night dog walkers and the like, and were able to put together an eyewitness account of the sequence of events. And the landslide started off with a small failure just above the sea wall. So round about 9 o'clock on the 3rd of June, Thursday night, small failure. By 11 o'clock, there had been a big failure. It had spread upslope, and it had spread around about 100 metres across the shore platform. And by early morning, most of the hotel garden had been lost as well. So what caused it? At the time, people would say things like, well, it was caused by really heavy rainfall following 2 months or so of really dry rainfall conditions. Well, this just really wasn't the case. And you can see from the winter rainfall, 1993 circled in red, below average for the winter, below average for the spring. And if you look at the 2-month antecedent rainfall totals going way back to 1970 when records in Scarborough began, that total has been exceeded 142 times since March 1970 before June 93. So what actually happened, what we believe was found in the boreholes drilled 10 years beforehand and immediately after the landslide. Now, borehole 2A down on the lower slope, that was drilled to treat a small landslide on the cliff face done by the council, and they picked up shear surfaces, shear planes within the mudstones underneath the glacial till at depth. Now, borehole 2 was drilled after the landslide event, and that picked up shear surfaces at 23 metres depth as well. Borehole 5 picked up the basal shear surface of the landslide, and it seems what had actually happened was that there had been pre-existing shears within the mudstones, and there had been progressive failure which had just developed through time. So there was no trigger, it was just the gradual reduction in strength of the slope. So the main focus of the early work was on the design of the coast protection measures, the emergency coast protection measures, and that was done really by Alan Clark and Steve Guest and other engineers at Rendell's. Roger and I's role really came a bit later when we're asked to look at the risk of a similar landslide occurring elsewhere within Scarborough's South Bay or North Bay. And in South Bay, we did geomorphological mapping, and we identified the location of 3 other major landslide systems there at the Spa, South Cliff Gardens, and Belvedere Cliff. Now, between them, there are steep, intact, unfailed slopes standing at around 35 degrees, and these were considered to be the potential sites of future major landslides. So, what can we find out about these pre-existing landslides? Well, it was off down the local library. This is pre-internet days, so no Googling or anything like that. It's going to the local reference library, opening up all the box files and see what you can find. And this guy, John Haynes, had produced a print of the landslide at the Spa, which occurred over the winter, over December 1737 into January 1738. The important things on this: the cows, there was a big block of land, the cows sank slowly for 15 metres. So it must have been, in contrast to the Holbeck event, which is going really quickly, this is sinking down, so the cows are, The spar at the cliff toe, the spar was heaved up by 5 to 6 metres, and it was displaced laterally by the order of 20 metres. Now that's really interesting. And look at all the pinnacled stuff in the detached mass. But equally amazingly, John Haynes had produced a cross-section before and after the landslide. The before is the grey line, and I've coloured up the after in red here. And you can clearly see what he was trying to sketch out was some form of graben development, with the cows slowly settling down as the graben forms and the main block moves laterally out towards the sea. And I suspect that this is the first example of a surveyed cross-section of a landslide, certainly in England. So what happened at the Spa? Compiling together boreholes drilled after the Holbeck event, so these are 150 years after the Spa landslide. The main feature here is that the cliff is composed almost entirely of glacial deposits, and the bedrock is at depth below sea level. But we can try and sketch on a crude model of what it might have looked like. Cows settling down, block moving out, probably on a compound surface like that. What do we know about the other 2 landslide sites in South Bay, at South Cliff Gardens and Belvedere Cliff? Not a lot, other than the fact that their morphology, their form, the form of the embayments appears on the first Admiralty charts of Scarborough Harbour from about 1843, and they're also on the map shown here, which is the first edition of the 6-inch Ordnance Survey map. At the time, we felt that these post-dated the Spa landslide because the morphology was fresher. It hadn't degraded as much. So, risk time, really simple equation, historical frequency, 4 events in 256 years, probability of another event occurring on the cliff line, 1 in 64, and probability of any single one of the cliff sections failing, about 1 in 250. This is the input model for the economic risk evaluation. Now, everybody's really happy. Rendals are really happy because we've done the first quantitative risk assessment in England for landslides. The Ministry of Agriculture are happy because they've got all the local politicians off their back and people are asking questions in Parliament. Scarborough Council are really happy because they've got a way forward and they can prioritise investment and things like that. Kids are happy. And this is my niece Kate, who made this cake for my, I don't know, what did we be, 30-something birthday. I dare not say what it was. But I'm kind of, it's starting to dawn on me that a simple division of X and Y might not be the best way forward for calculating probability. But this will realise itself a bit later. And it happens here in Algeria. And now we're in central Algeria on the Tadameh escarpment, and we're trying to route a gas pipeline up from the south, up from Insala, which is one of the hottest places in the world, up this escarpment and ultimately connect with the European gas system. This place is hyper-arid desert, so average 25 millimetres a year, but that's pretty meaningless because most years there's nothing, and then in a few years you're getting 100 millimetres plus, and that's all falling on a single day. But it's an amazing landscape of cambered jury crust and caprock blocks at the escarpment crest, and giant mega pipes on the escarpment slope. And in the bottom left, you can just see a tiny Chris Martin standing there for scale. And of course, monstrously big landslide systems, and you can see the back-tilted and displaced blocks there. Now, these landslides are believed to have originated in the early Quaternary. German research, not many people, nobody really knows much about the landslides in the Saharan escarpments, but German geomorphologists have looked at landslides in the Libyan escarpments and found that there had been 2 phases of reactivation during what's known as the African humid period, between around 5,000 BP and 8,000 or 10,000 BP. Now, the African humid period was the time of the Green Sahara. This landscape would have been savanna, there would have been giraffes and gazelle and things like that. It's the time of giant paleolakes, or what are now paleolakes, and also cave swimmers like at the Gilf Kabir in southern Egypt here. And if you remember the start of the main plot line of The English Patient, it's about discovering these cave paintings. Anyway, we're standing on top of the escarpment, and someone's saying to me, so, what is the probability of these landslide systems being reactivated? And he says, well, if they've gone twice in the last 10,000 years, surely it's 1 in 5,000 years. And I'm suddenly think, hang on a minute, this can't be true at all, because what has happened is that there has been an enormous climate change between the period when the landslides were reactivating and what is present now. And this is where this idea of changing process domains, landslides process domains turning on and turning off through time, started developing. And I remember going back that evening, and it started to dawn on me that what we had been doing in Scarborough really wasn't very sophisticated at all. So I started thinking about the relationship between classical probability, historical frequency, and what it actually meant for landslide systems. Now, a good starting point to explain all of this is the National Lottery. Now, National Lottery has 59 identical balls, and you repeat through time a series of identical trials. The balls don't change, the machine doesn't. I know they use different balls and they call them different names and all of that, but it's essentially the same. The trials are individual lottery draws. In reality, each ball has a 1 in 59 chance of being drawn, and then 5 more chances during the course of the lottery, because 6 balls are drawn. Each trial, and this is really important, each trial is independent, so it doesn't really matter what has happened in the previous trial, you can still draw the same ball in the next one. So imagine we're drawing the ball 21. The true frequency is approximately 6 times, because we're drawing them 6 times, it's approximately 1 over 59 times 6. In reality, it's 1 over 59 followed by 1 over 58, 1 over 57, and so on. And we assume that the observed frequency converges to the true frequency. We know what the true frequency is because it's a theoretical one over an infinite number of trials. So let's see how that works in reality. Since October 2015, there have been 893 trials. And what that means is each ball should be drawn by around about 91 times. But this is the actual number of occasions that individual balls have been drawn. Ball 21 here has only been drawn 79 times. Now, does that mean that you would put all your money on ball 79 next time? Or would you put your money on the balls that have been drawn a lot? 893 trials are not enough trials for the observed frequency to converge to the true frequency. So let's start thinking about how a landslide system, how a slope system actually works. It's a bit more complicated. We have a system state, which is essentially the slope, the geology, the geomorphology, and so on. And acting upon that, we have an energy regime, and that may be rainfall, seismicity, wind waves, and so on. And overall control of the energy regime are environmental controls, climate, sea level, and so on. So if we're looking at the situation like in Scarborough, we have 8 identical cliff sections, and we're running this system, these trials, independent trials, identical independent trials through time. There's a 1 in 8 chance of the event, if an event occurs, that it will occur in any one of those event sites. But we need to ask ourselves, are these individual cliff sections identical? And have they remained uniform over time? Have there been an infinite number of trials? And has the energy regime remained constant over time? And what we're doing with the energy regime is that we're sampling it on a year-by-year basis. We're assuming that there is a constant probability distribution, and you're sampling events out of that, and that the probability distribution isn't changing. The other thing that's different here is that the forms are persistent through time. Once a landslide has occurred, then it's always going to be remaining there until it's been removed by marine erosion or whatever. So let's think about the things that have been changing over the historical period. You've all probably seen graphs like this of sea level rise over the last century or so. Since Queen Victoria was on the throne, sea level has risen by around 20 centimetres. But what about sea level change over the last millennium? Now here's a chart of sea level rise developed from geological data over the last 1,000 years. And you can see significant changes going on here. So from the time of William the Conqueror all the way through to the murder of Richard II and Bolingbroke landing at Spurn, and so on, sea level fell by over 10 centimetres. It rose again from Agincourt to the Armada, Drake and Hawkins and the like, the defeat of the Spanish, and then through the Gunpowder Plot, all the way through the French Revolution and so on, Crimea War, sea level was falling again, and then we're back up through time to the present day acceleration. The star is where the time that the Spa landslide occurred in 1737-38, in a time of falling global sea levels. What else has changed? The energy regime at the cliff foot has changed, and the obvious thing is because of the seawalls. The first seawalls were built in 1850 at the Spa, Holbeck Hall, Holbeck Gardens around 1890, and then the intervening sections just before the start of the First World War. Now this has a really important and dramatic impact on the cliffs because it's transformed the systems from actively eroding to effectively abandoned cliff lines. And the dominant processes have changed from removal of debris and undercutting by marine erosion to one where weathering, poor pressure recovery becomes important. So significant changes in process domains. Climate has changed. This is the Central England temperature record dating back to 1659 to present day. And you can see the dominant trends through here. The only thing that I've added through this is a 10-year moving mean through the data. Often the data is plotted relative to a baseline, and in this case, it's the 1961 to 1990 baseline. So years that are warmer are shown as positive anomalies, years that are colder are negative anomalies. And you can see some basic trends in this. Down around the 1700s, really cold compared with today, and then the modern potential warming over the last 20 or 30 years. And in between, well, you're playing eye of faith about whether it's wiggling up and down or there are serious trends in there. Precipitation, this is the England and Wales precipitation series, which goes back to 1765, but less precise data goes back to 1727. Again, plotted as anomalies against the baseline, and we can see much drier round about in the early 18th century, and then the hints of being wetter in present day. Now we can use these anomalies to plot out simple climate charts, and it can be cold and wet, warm and wet, and so on. Along here, the x-axis are the temperature anomalies, and the y-axis are the precipitation anomalies. And let's see where the individual years are plotting. So back in 1727 to 1765, add on another 50 years till the end of the 18th century. And then we have present day, sticking out above the warmer and wetter period. Let's think about when those landslides happened. 1737 is plotting down effectively almost average conditions, and Holbeck 1993, again almost average conditions. Not what you might expect. You might be expecting that the warmer and wetter conditions were associated with the landsliding. Using this information, we can start dividing the timescales that we've been working with up into a series of different slots. So we can do it in a simple, crude fashion, 1700 to 1800, generally cooler and drier climate than compared with today, with slowly falling sea levels, but still with episodic toe erosion. Then from 1800 to 1900, generally cooler and drier compared with average, slowly rising sea levels, but still active toe erosion. 1900 to 2000, pretty average climate, but we've built the sea walls now, so we've prevented marine erosion, but sea level is still rising. And then 2000 to present day, warmer and wetter compared with 61 to 90, but with accelerating sea level rise and no toe erosion. So we talked about the energy regime not being stable through time. What about the cliff sections themselves? Now here is a plot of all of the borehole data drilled after the Weddepohl landslide, and you'll see on the map down in the bottom right-hand corner, all the individual dots represent boreholes. On the plot, across the top, you've got the individual cliff sections, so Weddepohl on the left, all the way through to the spar on the right. The red shading is picking out the pre-existing landslide sites. The scale down the left is running from 60 metres OD all the way down to -20 or something like that. Thing that sticks out, the bedrock profile is dropping from around about -35 to 40 at Holbeck, all the way down to below sea level at the spar. The materials are shown. Browns would be silty sandy clays, stratified diamictons or boulder clays. In yellow, we've got sands and gravels, but in blues, there are laminated silty clays and clay silts. The bedrocks, siltstones, mudstones in green, limestones and sandstones. We can split up the cliff line. So Holbeck Cliff in the south comprises essentially silty clay diamictons over weathered mudstones. In the centre we've got essentially boulder clay cliffs over siltstones and sandstones, and then falling down to the spar we've got essentially a profile dominated by sands and gravels and sandy silty clay boulder clays all the way through the cliff. So the cliff units are varying as we move along. So let's get back to our simple model, and we ask ourselves, clearly the energy regime has changed through time. The cliff sections are not uniform. The historical record is not the product of an infinite number of identical trials. The trials are not independent, because we've got a system memory that once a landslide has occurred, we can't utilize that site again. The observed frequency is not a true frequency, a property of the system itself. It's just statistics, and it ignores the important geology and geomorphology. So, which brings us back to the simple model we had at the beginning. Using steady-state equilibrium assumptions, the reality is probably that individual landslide events reflect unique combinations of circumstances rather than them being a series of random events through time. So they're all reflecting, in my opinion, individual circumstances. In terms of the past and present being the key to the future, the timing and magnitude of future events is probably uncertain. You think of, standing on the cliff line before the Weddepohl landslide occurred. The biggest event that had happened was the Spar landslide, which sunk down so slowly that the cows were still grazing there, and they only lost 30 metres of cliff top overnight. The next day, you've got a landslide which is completely different. It's running out 100 metres over the space of a few hours, and you're losing 90 metres of cliff top. Okay, time to move on. We're then moving down to Holderness. Glacial till cliffs. Probably the fastest eroding cliff line in Europe, but also one which has been blessed by the fact that the local authority established a network of monitoring posts back in 1950. So we have continuous annual records of cliff recession since 1951. You can see where the data can be gathered from. It's easily accessible. The main issue, obviously, on the Holderness coast is loss of property, clifftop property. And here I am. I'm sat in the front room, or really the back room, of one of these houses in Ulrome at the northern end of the Holderness coast. I'm drinking tea, eating biscuits with the retired couple who are living there. They'd bought the house in the expectation that they would be able to see out their days there. Their local estate agent and solicitors had told them that the cliffs were eroding at 0.7 metres a year. But over the course of the next 5 years after they bought it, they'd lost 20 metres of their back garden. The coastal road had been lost. The back garden was almost completely gone. And they were hoping to sue the local estate agent for it. So I'd say, well, good luck. And then went on to try and explain to them that although you've got an average rate, what really happens is that you have long periods of not a lot happening, punctuated by short periods of intense erosion activity. They said. That doesn't help, and they were very disappointed in me. But it does highlight one of the problems that we have in predicting cliff recession rates. And the traditional way of doing the cliff recession risk would have been to set up erosion contours, stepping back inland 10 years, 25 years, 50 years, or whatever. Now, the economic risk, say for the farmhouse, which is going to be lost in 25 years' time, is simply the market value of that property times a discount factor for the year in which it's been lost. So the year of loss is important. But one of the problems is, what is actually the recession rate that you're going to be applying for the cliff recession loss? And if you look at the chart here, these are recession rates calculated decade by decade. And they're all different. And what it shows is that the recession rate is incredibly sensitive to the time period that you choose. And a decade has got no physical significance whatsoever. You know, geological systems aren't working from January the 1st, 1 year to, December the 31st, 10 years later. The other problem is, what about the variability? And here is a magnitude frequency curve developed for the whole of the Holderness cliff line, and it's showing the number of records on the y-axis and the event size, or the recession event size, down the bottom. And events can range from anything from 0 recorded in a year all the way up to 24 metres in a single year. So to get round this, we developed a probabilistic model. So rather than deterministic projections of erosion contours through time, we took a magnitude frequency curve. This one developed between erosion post 60, Hornsey, and about 86, which is Withensea on the coastline. And we sampled it multiple times. So you're drawing out a recession for each year on a single pathway according to the probability distributions. Do that time and time and time again, and you end up with multiple pathways, and you can create a probability distribution from that. This was done for the Ministry of Agriculture. Everyone's happy again, but it still suffers from essentially the same problems that we had in Scarborough, that you're assuming that the conditions have remained constant from 1951 to 2020, and that the cliffs are uniform all the way between erosion post 60 and 86, Hornsey and Withensea. So let's have a look and see what has actually happened. This is the tide gauge for Immingham. So Immingham's on the mouth of the Humber, so just south of the Holderness Cliffs. Sea level has been rising there in the order of 0.7 millimetres a year. So broadly consistent with expected trends around the country. At the same time, the cliff recession rate has been on, for the whole of the Holderness cliff line, has been increasing as well. So cliff recession is influenced by the rate of sea level rise. And we worked out that for every millimetre of sea level rise, there had been a 1.1 to 1.6 centimetre increase in the recession rate. So it's gone up from something like, on average, 1 metre a year in the early 1950s to close over 2 metres a year present day. What about the cliffs themselves? Are they uniform? Well, at Aldborough, Holton, Dimlington, very variable coastal deposits in the cliffs. Cliff height varies a lot as well. Holmton cliffs are about 13 metres high, Dimlington 23 metres high. Interference by coast protection works has been another factor which is inducing non-uniform behaviour in the coastline. Here the chart is turned over, so north is to the left. The dominant drift direction is from, on the picture is from left to right, north to south. And here you can see at Hornsey, on the right-hand side, downdrift of the groin fields and the sea wall, we've got accelerated erosion. And on the updrift side, you have accretion and reduction in the recession rate. This is Coastal Engineering 101, so there's nothing surprising here. But what it's doing to the cliff line, this is the whole of the cliff line, erosion post 0 to 120, so left is north, right is south, recession rate are on the others, the y-axis. At Hornsey, erosion post 40 odd, Withensea 86, and then Dimlington further off to the right. You can see that it's having a real impact on the coast with a declining trend of recession rate induced downdrift of the coast protection works. And there's a cell forming, coastal cell forming between Hornsey and Withensea and between Withensea and Dimlington. That's interesting. But let's have a look at what the cliff recession used to look like before the defences were put in. And this is a chart on the left-hand side for recession rates measured, and people were actually measuring rates back in the 18th century, rates between about 1775 and 1852. And you can see a very different pattern of recession here. You still get the variability, but there is no cell fragmentation. You might expect that the amount of recession you get is directly related to the energy inputs in a single year, the storminess. And it might go something like this, that the more energy that we put in through storms, the greater the recession rate. Unfortunately, we've got no direct measure of storminess by year on year from 1950, but what we do have are measures of the North Atlantic Oscillation. Now, the North Atlantic Oscillation is kind of like the Atlantic version of El Niño, La Niña climate system. And the North Atlantic Oscillation Index is a measure of the difference in atmospheric pressure between Iceland, and the Azores further south. And here is what they call the Hurrell North Atlantic Oscillation Index from 1950 onwards, and you can see series periods when the index is positive, periods when the index is negative. A positive NAO index is associated with strong southwesterly winds, but also warmer and wetter conditions, so associated with storminess in the North Sea. The negative index is associated with weaker southwest winds, colder and drier conditions, cold northerly winds blowing off the North Sea. So let's see how these two relate. Across the bottom, we've got the the NEO index, and on the y-axis we've got the recession rate, and there's virtually no relationship between the two at all. So, well, that's confusing. What about recession? When would you expect the biggest recession to occur? Maybe during those years where storm surges happened. And we've had 4 major storm surges since 1950. The obvious one is 1953, the East Coast floods, when 307 people were killed on the east coast of England, many, many, many more in the Netherlands and Germany. But we've also had storm surges in 1976, 79 and 2013. And the 2013 one was actually much higher than the 1953 storm. The obvious difference is that the coastal defences have been improved since then. So let's look at the annual recession in those years where the storm surges occurred. And there's clearly they're not peaking in those years. The only year when they're above average is the 1976 period, and that's certainly not comparable to the years with the fastest erosion. So what's going on? How can we explain this? And to understand, we need to start thinking about the role of the beach in dissipating wave energy on the foreshore, a system state condition. Now, on the Holderness coast, you have this arrangement of sandbars in the intertidal zone, and behind them there are troughs called ords. Now, occasionally the ords intercept the actual cliff line, and where that happens, you get the cliff foot exposed much lower down, and the waves can penetrate in and cause, in theory, much more erosion. So we're talking about the development of recession hotspots where the ord is actually intersecting the cliff line. Now, the general idea is that the ords migrate in a steadily fashion, 400 to 500 meters a year southwards through time, creating these hotspots which then migrate southwards. And the model would look something like this. You have the hotspots in red, and year on year they're just moving southwards a little bit. That's really convenient. But the reality is something more complicated. Now, here are the recession rates, the recession values between erosion post 60 and 80, so Hornsey to Withensey again, 2000 to 2020. The red cells are those years in those locations where greater than 3 meters of recession have occurred. So these should be the hotspots. And your eyes can be drawn to any sort of line through this, but certainly not really simple migrating hotspots. So what's going on? Would that it were so simple. The impact of wave energy at a moment in time is contingent on the system state at the time of the event, of the storm event. And you may have an ord, you may have landslide debris on the foreshore, there may be preceding undercutting. And the other factor, of course, is that as we're retreating back, we're exposing different geologies as well. 2 identical storms can have different impacts through time. So the same magnitude storm may result in different levels of recession. The response to storm events depends on the conditioning effect of previous events, and this is known as morphological conditioning, or the cliffs having a memory of what has happened in the past. And because the output from the system, cliff recession events, is really heavily dependent on the conditions of the system state, this sensitive dependence on the initial conditions is a feature of chaos. Now, in my mind, chaos and chaotic behaviour is a real potential for many of the fast eroding cliff lines that we have around the country. So back to our simple model again. Steady state equilibrium. Well, cliff recession is contingent on past events. The history matters. The future, past and present are the key to the future. The future response to relative sea level rise is uncertain, and it's probably non-linear. I know you can imagine a situation where you just put an extra bit of sea level rise in and you get a commensurate amount of increase in recession rate. But imagine a situation where the response curve is non-linear and maybe accelerating the response. And so, time for reflection. Where have we come from? So, we've focused on the Yorkshire coast, but the Yorkshire coast, despite being wonderful, is actually a window into landslide systems anywhere in the world, because they're all basically made up of the same components. You have a system state, and that's controlled by the geology, geomorphology, and so on. And that system state isn't constant through time. It bears the imprint of past events. It also, so that's its memory, but it's also subtly changing through time as it weathers and so on. We have an energy regime. That may be on the coast, it's rainfall and waves, but you also have earthquakes, seismicity, and so on. And we have environmental controls. And the environmental controls, no matter where you are, they're changing through time. Now, what is really important is what is the time scale that is relevant for these changes in time and changes in system state. Radical uncertainty and landslides, where does the radical uncertainty really come from? Partly it's due to the nature of physical systems, and systems can range in complexity from something like the solar system, where the movement of the planetary bodies are governed by simple laws and it's almost completely predictable. We can land men on the moon without getting lost. We can send probes out to Neptune and beyond and still get there, and the planets will still be there. All the way through to economic systems, which are inherently complex. Nobody here would guess, if I said the interest rate is going to be 6.3% in 7 years' time, you just wouldn't believe me. That would be your experience, that these systems are so complex that some form of prediction just isn't practical. And I think that our physical systems, our landslide systems, are sitting somewhere in between these two different M members, possibly closer to the economic system in some cases, maybe closer to the solar system in others. So radical uncertainty comes from a combination of system behavior, the occurrence of morphological conditioning, so the memory of past events, but also the complexity of the response to an individual storm event or so on. We also have uncertainty arising from what you could call system specification, and this is related to the strength of knowledge we have about the system. We may feel like we completely understand how a system works, but we will never have enough information to precisely predict the future conditions, because the models are so sensitive to small changes in parameters. And of course we have environmental controls changing through time and changing process domains as well. The greater the degree of geological control, the greater the importance of deterministic uncertainty and chaos. So what are our lessons from Yorkshire? And we can apply to areas which have got longer timescale event occurrences. So in Yorkshire, we've had non-stationary energy regimes, human intervention, time-dependent internal slope processes. multiple process domains across the historical record, and the probability that the individual events are one-off events and not part of a random series through time. Statistical extrapolation from historical data sets covering different process domains through time can yield misleading results and not objective truths about a system. But on the other hand, estimates of landslide probability which incorporate geological information like the boreholes and the geological knowledge from Scarborough will typically be subjective judgments. And the problem with that is often, and I guess you've all experienced this, that different experts will have different opinions, even using the same data. So faster moving systems, 1 to 10 year timescales. Here we have non-stationary energy regimes, the importance of human intervention, coast protection works then on Holderness, short-term variability in system state, no clear relationships between forcing, wave energy input, and the response, the outcome. And the response is contingent and dependent on the initial conditions of the system. In the case of setting up erosion contours or probability distributions based on historical data, they're unlikely to accurately predict the future, particularly to the response to future rates of higher sea level rise. And in my opinion, knowledge of complex system behaviour should be incorporated into recession models. And here we're talking about understanding the importance of positive and negative feedbacks within the system, and also the deterministic uncertainty. Say, for example, in this simple cliff recession model here, we don't actually know in any great detail how much sediment is retained on the beach once it's been supplied by cliff recession, how much is output from the system, and whether that changes with the storm conditions and so on. And this is the deterministic uncertainty, which is part of the problem. It's the end of a long day, end of another long day. You probably gathered, I'm a geomorphologist. Yeah? So my message to you is really to say that engineering geomorphology is more than simply mapping landslides. I know that Jim and I first started out on the Channel Tunnel many years ago, mapping the landslides there. But my work, and I think the work of many other geomorphologists, has changed over time, particularly with the integration into risk assessment, whereby we're now looking to try and understand how systems work in a practical way to guide risk assessment and risk-based decision-making in the future. So, thank yous. Well, I've worked with thousands of people during my career. I can't say thank you to everybody. So you know who you are, so thank you. But this bloke, Peter Fuchs, many of you know Peter. Peter is really, really important for me. Peter and I worked together very closely for nigh on 20 years. Two important memories from Peter. Peter would always say his work was his hobby, and he would always take every assignment that we did as if it was an adventure holiday. And I learned, and I hope I'll carry on Peter's tradition of work is fun into the future as well. But Peter is also important because he talent spotted Dennis Brunsden back in the 1960s. Dennis was an academic geographer at the time, but Peter got him mapping landslides in South Wales and then in Nepal, and he encouraged Dennis and his John Dornkamp and Ron Cook and David Jones to set up geomorphological services. No geomorphological services, no me, no Jim, no Roger Moore would have all had different career pathways. So Peter directly and indirectly, really important. One last person to say thank you to. So the boss, my wife Claire, practically perfect in every way. So thank you, everybody.
Thank you, Mark. I'd like to invite David Wareing to come and give the vote of thanks. It's hard to see people here. There you are, David.
Good evening, Chair, esteemed guests and colleagues. It's a great honour for me to deliver the vote of thanks for the 24th Glossop Medal Lecture, Landslide Risk Assessment, Radical Uncertainty and Engineering Geomorphology by Mark. I'd like to begin by expressing my sincere appreciation to Mark for tonight's stunning and thought-provoking lecture. As we've seen, landslide risk assessment is a complex endeavour. Mark has demonstrated the vital role of geomorphology, geology and an understanding of slope behaviour in landslide risk assessment, bringing his points to life with compelling cases of Weddepohl and the Holderness Coast. Through these examples, he's highlighted the challenges in predicting rare, episodic landslides and the unpredictability of an evolving coastline. I especially appreciated Mark's lightbulb moments when he realised that relying on past failure frequencies can lead to misleading predictions of future events. His use of analogies from Manchester United and the National Lottery showcases talent for making complex ideas accessible to non-specialists. How do I know Mark, you may ask? Well, I first met Mark 20 years ago on a field trip to Georgia, far from the Yorkshire coastline, in the Lesser Caucasus Mountains. Our task was drainage mapping along the routes of two pipelines that would span from the Caspian Sea to the Mediterranean. With just 2 weeks to assess a landslide-prone corridor, our first hurdle was convincing the client that red overalls, hard hats and steel toe-cap boots weren't ideal for alpine terrain. Luckily, we won that debate in favour of the more customary floppy hat, walking boots and jacket. From our first collaboration, Mark's exceptional talent as an engineering geomorphologist was clear. With a legacy shaped by mentors like Peter Fuchs, Dennis Brunsden and Jim Griffiths, Mark's deep knowledge allows him to read terrain, evaluate hazards, and articulate risks with ease. Just like his mentors, Mark has been generous in sharing his knowledge and expertise with the next generation of engineering geologists and geomorphologists. If you ever have the chance, I strongly recommend attending one of his renowned field trips, and if you're lucky, you might get to share the experience with one or more of his beloved greyhounds. In 2016, Mark and I once again collaborated, this time in Oman's Asamin, a salina, also known as the mother of poisons, for another BP project. This time, kitted out in red overalls, but still with our floppy hats, we crossed the salina, hand-digging pits and auguring in extreme heat. The visit remains unforgettable, capturing the spirit of exploration as we retrace the steps of Thesiger, likely the first European to cross the salina in 1949. Mark's concise summary presentation to the project team in Muscat was masterful. Clearly outlining the project's hazards and risks, it laid a solid foundation for subsequent civil and geotechnical efforts. His ability to communicate effectively with both specialists and non-specialists is one of his greatest attributes. This talent is also evident in two notable QJEGH papers co-authored with the late, great Peter Fuchs, the Engineering Geology of Players, Salt Players and Salinas, and the Engineering Geology of Concrete in Hot Drylands. If you haven't read these, I highly recommend them, especially for anyone with the good fortune to work in a hot, arid environment. In closing, I want to acknowledge Mark's dedication, expertise and collaborative spirit. His work has deepened our understanding of landslide risk and inspired many of us. Thank you, Mark, for your invaluable contributions and for sharing your insights with us tonight. Chair, esteemed guests and colleagues, please join me in thanking Mark for an outstanding 24th Glossop Medal lecture.
Thanks, David. Thank you, Mark. So we move on now to presentations, and if I could invite Emma Slack, representing Rudolph Glossop's family, to come up and give some presentations, please. So we'll start with the presentation for the 2024 Early Career Glossop Award to Jordan Weddepohl. So I think we've got the certificate and the hammer. Well done, Jordan. And then moving on to the presentation for the 2024 Glossop Medal to Dr. Mark Lee. You can sit down. Yep. Emma, thank you. We've got some token of our appreciation. Thank you. James has got some flowers. Thank you very much, Emma. Thanks. We're very grateful for the continued support from the Glossop family. So just now over to some wrap-up notices, some thank yous and the close before we can all go for dinner. So firstly, apologies, it's so cold in here. I don't think they're trying to save carbon. We will be asking for a discount. But I think we've got some rolling slides with some more information on coming up, but a reminder that you can engage with EGGS and our Active Early Career group on LinkedIn, where you'll find our quarterly newsletter with our upcoming events, including monthly evening meetings hosted around the UK, and they're usually hosted as hybrid events. We've got notice come up there of this is early notice of our annual conference hosted again back in Cambridge. This year, the theme is the engineering geology of the energy transition, and it includes a dedicated time for the book launch and associated talks from the upcoming special publication on offshore site characterization, which is the work that Chris Martin and his team are leading for EGGS. So now it's my pleasure to announce the next Glossop lecturer for 2025. So the Glossop lecture for 2025 will be presented by Dr. David Giles of Card Geotechnics Limited and formerly Portsmouth University. Dave's Glossop... Oh, another clap there. Well done, Dave. No, it is in writing. He's committed now. So Dave's Glossop lecture will be wrapped around the inaugural Fuchs meeting for engineering geology, which will be hosted at Burlington House, and that's been enabled by an endowment from the Fuchs family. We'll send out more details about that. So finally, on to the thank yous. So thank you very much to all our sponsors, to Soccertech for sponsoring the award, to Atkins Realis for sponsoring the theatre. They should ask for a discount. To Jacobs for sponsoring the AV, our event sponsors, ACOM, Arup, Coffee, Covey, GEA, Geobroke, Landmark, Mott MacDonald, OWC, RSK and SatSense. Do a little clap for them, a little clap for the sponsors, thank you. So thank you as always to the staff from the RI for hosting us so well as usual. Thank you to the AV team up there and up there. Thank you very much. They've been live streaming this event as well, so thank you. And thank you to the dedicated Eggs Committee, and in particular James, Josh, Steph and Millie, who have done a huge amount of work over the last year to pull this event together. So, thank you. Thanks, guys.